After the discoveries of Edwin Hubble early in the 20th century on galaxies and the expansion of the universe, astronomers continued their research into these areas during the mid-20th century. They began to learn more about the distances and sizes and masses of galaxies and many of their other properties. And all seemed very straightforward. However, in the 1970s, new measurements provided a startling new insight into the basic structure of galaxies, and that's the topic of this lecture. During this time period, a young astronomer named Vera Rubin was doing research on the rotation of the Milky Way galaxy. She was doing this in order to better understand its gravity and therefore its mass distribution throughout the galaxy. So Rubin was measuring various objects throughout the galaxy to see the velocity with which they rotated around the center of the galaxy. And essentially, her research indicated again a very new and startling result. Although most of the visible matter and most of the light in the Milky Way came from that central bulge and from that disk, well, her measurements of rotation velocities indicated there had to be far more mass in the Milky Way than was visible. How did she determine that? Well, when we consider a system perhaps like our solar system with the sun in the middle and the planets orbiting it, you may know that as the planets orbit the sun, they each orbit at a different velocity. The farther out the planets are from the sun, the slower they orbit. We could say that their velocity decreases as their distance increases. Why is that? Well, because in our solar system, nearly all of the mass or matter is concentrated in the sun, in the very center. Now, at first, we might assume something very similar for a galaxy. We do see most of the visible matter in the center, in that central bulge. But this was not what Rubin found. Her measurements indicated something different. Basically, what she found was the rotation speed of the Milky Way did not decrease with greater distance from the center. Instead, it stayed relatively uniform. If we were to graph that out, we would get a very simple graph showing, again, a very flattened curve. So this indicated to her that mass was far more spread out in the Milky Way than was visible. Well, this was, again, a very surprising result, and over time other astronomers, of course, would verify this. It turned out that there was many times more matter in the Milky Way than was visible. Well, Rubin and other astronomers next turned their attention to other galaxies, measured their rotations, and sure enough found that they also had very similar results. These other galaxies also gave indications that they were surrounded by this invisible matter that we couldn't see in a roughly spherical shape. In other words, most of the mass was in the halo of the galaxy, even though we couldn't see it. Well, this was quickly dubbed dark matter. And I'd like to emphasize that it's important to realize that it was not only dark or invisible wavelengths that you and I might see, but really in any wavelength of light. We could not detect this matter in ultraviolet or infrared or any other type of radiation that we're familiar with. We simply found nothing. Again, how did we know it was there? Really from the gravity of this matter in the Milky Way. It was changing the rotation of the galaxies. Well, as time went on into the 1980s, 1990s, astronomers began looking for other ways to try to confirm this discovery. It's often good in science if you can have an independent means to verify a discovery. So they looked out into various rich clusters of galaxies, carefully measured the motion of galaxies within the cluster to get an idea again of their relative speed and really how much gravity was in the cluster. Well, they found that these galaxies were moving quite rapidly within their clusters, faster than would be expected. What do I mean by that? Well, these galaxies were moving so fast that really they should be leaving the cluster. Something clearly was holding them in. What was that something? Well, this had to be the additional gravity of dark matter. In other words, when astronomers would measure those velocities, that would tell them there had to be additional mass than what was simply visible. Another discovery confirmed the existence of dark matter. Here we did turn to other wavelengths, perhaps ultraviolet wavelengths and others, and besides seeing stars in the galaxies, we began to find much hot gas in these clusters of galaxies. And when you think about the high temperature of gas, that means that each particle in the gas is moving at a fairly high velocity. Well, once again, when you consider that if the particles are moving at a high velocity, they should be escaping from the cluster, but they're not. We see the concentration of gas there in the cluster. So the point being that this high temperature of the gas told us there had to be more gravity holding the gas in the cluster than could be accounted for by the visible matter. And so as a result, this was yet another confirmation of dark matter. Yet another line was pursued to establish and confirm dark matter, and this has to do with Einstein's theory of relativity. You might be aware that his theory states that powerful gravity can actually bend light as it travels. In other words, as a light ray travels past a massive object, it will be bent or distorted. Well, picture now, for example, a cluster of galaxies, and yet in the distance would be galaxies perhaps behind that you and I might not normally see. Well, the light from those distant galaxies, as it passes through the nearby galaxy cluster, would be bent. It would be distorted in a certain predictable manner that we could look for. And sure enough, astronomers found this effect. When we look at clusters of galaxies, we often will find streaks of light around the cluster that is the distorted light from galaxies behind the cluster. And as a result, we have a way to measure the amount of gravity in the cluster. And clearly the amount of gravity would depend on the amount of matter. So the point being, this so-called gravitational lensing is a powerful method for us not only to confirm extra mass that we can't see, but to actually begin to measure it in a sense. In other words, the amount of the bending tells us the amount of gravity and therefore the amount of mass, and sure enough, it's far more than there is visible mass in the clusters. So this was a major discovery in the late 20th century and has continued to intrigue astronomers to this day. So what is this dark matter if it doesn't give off any type of light? Well, astronomers considered many possible options for this. At first, some very obvious ones came to light. You might think of extremely dim stars, or perhaps lots of planets floating through the universe. And these became known as massive, compact halo objects, or MACHOs. And this could be, again, extremely dim stars. Astronomers had discovered some called brown dwarfs, which truly aren't actually stars because they don't quite get hot enough for that thermonuclear fusion in their cores. So these are very cool objects. They go off very little light. Could that be dark matter? Well, it turns out there simply aren't enough of them. How about white dwarfs? We learned earlier in our course that there's probably many, many billions of white dwarfs, the remains of old low-mass stars. Well, once again, even though they're quite dim, there simply isn't enough of them. How about neutron stars or black holes? They don't hardly give off any light at all. Once again, there's not nearly enough of them. So it appears that dark matter is not actually composed of large objects like stars. Well, if it's not large objects, astronomers considered the possibility it could be smaller objects, perhaps particles. And so they've looked into this in recent years. If there were certain particles of just the right properties, these might explain dark matter. Now, of course, there would have to be an enormous number of these particles. These particles cannot give off light. In fact, they would not actually interact with other matter in any way other than gravity. They would not feel the electromagnetic force or other such forces. And interestingly, as we'll see later on, when astronomers began to develop theories of the beginning of the universe, it may be that these particles could have been produced early in the beginning of the universe with the right properties to explain what we see today in dark matter. So here's where the focus has been in recent years, on these particles, weakly interacting massive particles, or WIMPs. And at this point it appears the WIMPs have the upper hand over the machos. Well, what other effects might we see of dark matter? If we were to look carefully and measure carefully the motions of galaxies through space, subtracting out the expansion of space, we would notice galaxies moving in very interesting patterns, usually towards great concentrations of gravity, which of course betrays great concentrations of matter. In fact, other theories of galaxy formation have found that dark matter is actually a great aid in explaining the formation of galaxies. In other words, with our standard model of simply visible matter, we don't really have enough matter, we don't really have enough gravity to really form galaxies as quickly as they did in reality. And so in this sense, dark matter is an actual aid to our understanding of galaxy formation. In other words, without dark matter, it's somewhat difficult to explain how galaxies formed. As we look out into space, we also notice how galaxies clump together. We've mentioned clusters, and we'll find that they even have clusters upon clusters upon clusters, forming what we call superclusters of galaxies. Now, these superclusters are of enormous extent, but again, it's somewhat difficult to explain their existence without the extra gravity of dark matter. And so today our models of the formation of galaxies that include dark matter do a much better job of explaining their existence than our early models without dark matter. Well, if dark matter is so prevalent and such a major source of gravity, might it have affected the entire universe? That's a very good question, a very important question if we're going to understand the entire universe. In fact, when you think about it for a moment, as the universe over long periods is expanding, you would have the gravity of not only visible matter, but dark matter resisting that expansion. Galaxies would tend to be pulling back towards each other even as space is trying to push them outward. So in other words, dark matter could have an effect on the expansion of the universe. Well, there's really three possibilities that we want to consider here in this regard. Our first possibility is that there would be so much matter, so much dark matter, that it would slow the expansion, perhaps even to the point at which it would stop, and then our galaxies would begin to move back towards each other. That, of course, would require quite a bit of dark matter, wouldn't it? On the other hand, we could have a scenario where the expansion would slow due to the gravity of dark matter, but it would continue to expand, perhaps at a slowing rate over long periods. And finally, there could be a scenario where we would have a certain amount of dark matter and normal matter, but it really wouldn't have much effect on the expansion. It would be a steady expansion. So as you look at these three models here, you can see the differences that are illustrated in these three cases. Well, how could we possibly determine which of these might be true? Certainly it depends again on the number of observations we can make to measure the expansion rate, and that would be determined, of course, by the amount of gravity. So in other words, astronomers would need to measure the expansion of the universe at different points in time. This would then tell us how much of an effect dark matter is having. Well, when we do some simple calculations, it turns out there's not nearly enough visible matter to slow the expansion of the universe, and so you might think, well, in that case, it would be a matter of the dark matter playing the vital role, and that would be correct. Really, you could say the future or the fate of the universe, so to speak, would depend on how much dark matter there is. Well, even when we add in the amount of dark matter that we're aware of, it turns out there doesn't seem to be enough to stop the expansion. In other words, there's not enough density of matter, we might call it, to reach that critical point to stop the expansion. And in fact, it's exactly what astronomers call it, the critical density of the universe to stop expansion. Well, again, how could we confirm that? Could we go out and perhaps again measure the expansion, let's say today, 1 billion years ago, 5 billion years ago, 10 billion years ago? How could we do that to distinguish between our different models? Well, two teams took it exactly upon themselves to do just that. Back in the 1990s, they wanted to go out and measure that expansion at different epochs during the universe history. Their result was completely astonishing. Interestingly, both teams found the same result that completely surprised the entire astronomical community. Not only was the expansion not slowing down, it was speeding up. In other words, the expansion of the universe was accelerating. This was quite a shock. At first, there was no explanation for this. The results were checked, the measurements were recalculated, and both teams were quite certain of what they had found. In fact, they both received the Nobel Prize for this discovery. What could possibly make the universe expand faster over time? Well, to this day, we still don't know exactly, but in the meanwhile, we've given it a name. It's called dark energy. Some unknown type of energy that is causing the universe to expand faster and faster over time. So really, I think you can see that the future or the fate of the universe not only depends on dark matter, but on dark energy, doesn't it? So now let's discuss a little bit more about this second major find. How did the teams measure the expansion rate? Well, you'd need to be able to measure the velocity of objects over a certain amount of time to get an idea. And what they chose to use is a very well understood use of a type 1 supernova. Now you might recall a type 1 supernova is when a white dwarf goes over its limit and explodes. And importantly, the white dwarf will only explode when it has that exact amount of mass. You might recall that was 1.4 solar masses. So the point being that every time a white dwarf supernova goes off, it has the same mass and therefore the same amount of energy, which implies the same luminosity. So here we have what we call sometimes a standard candle, an object that always has the same luminosity. Well, I think you can see where I'm going here. If we have such an object, we could use it to measure distances, couldn't we? If we know its luminosity and we measure its brightness, we can find the distances. So the point being, astronomers would look into the distant early universe for these type 1 supernova, and when they would see one, they would know its luminosity, and by measuring its brightness, they could determine the distance. And if they knew when this occurred during the history of the universe, we could determine the rate of expansion. Well, what both teams essentially found was that the supernovae were dimmer than expected. Now, of course, they had to go back and make sure we understood these correctly, but the point was, if they were dimmer than expected, wouldn't that imply that they were farther away than expected? And think of it this way. The greater distance in the same amount of time implies they had to have been moving at a greater velocity. But when would that have occurred? Well, we have to actually kind of turn it around and think more in terms of, in today's universe, we have moved farther away from those distant early supernova because today's universe is expanding faster than it was in the past. How can we illustrate that? Well, I'd like to show you a chart that just shows us a few simple numbers here and will help us understand that. Let's measure the velocity of a hypothetical galaxy at various distances. For example, if the radial velocity of a galaxy at 1 billion light years distant is perhaps 1,000 kilometers per second, I'll just use some simple numbers, what would the velocity be at 5 billion light years? Well, as you can see here, if the velocity was less, clearly the expansion is slowing. And our universe may actually slow down and contract, wouldn't it? If the velocity was still 1,000, well, clearly we would say the velocity is not changed. It's a very steady expansion. But If we measured the velocity at perhaps 1,500 kilometers per second, clearly we could say it has increased. The expansion rate has accelerated. So the point being, again, that a greater velocity, this greater distance, means we're the ones moving away more quickly in today's universe, and the expansion rate is accelerating. Now we could draw a simple graph that illustrates this as well. Astronomers have done that. This very simply shows several different models of our universe. In red, you see a recollapsing universe that has a great amount of matter where the expansion slows and eventually stops. In green, we see a critical universe where the expansion gradually slows but never stops. In blue, a coasting universe where the expansion is steady, and yet look carefully at that top yellow line. That would model for us an accelerating universe. Now look closely at the various dots. These represent the actual measurements. I think it's clear that you can see the measurements follow the yellow line best. The expansion rate is not constant, is it? But greater distance in the same amount of time means we have a faster expansion rate today. So by now the actual expansion rate has been measured carefully and confirmed many times, and this is a reality of our universe, that its expansion is accelerating. What other evidence might there be besides the measurements of supernovae distances? Well, when we map out the sky on vast distances, we see again this filamentary or kind of clumpy structure, we call it. And yet when we model that on a computer, our best matches include dark energy. Why is that? Well, if we had a universe with only dark matter, we would see even more clumping of galaxies, more filamentary structure. But we see a moderate amount of clumping and structure. Why is that? Because dark energy has the opposite effect. It wants to tend to spread galaxies farther apart. So there's a balance here. The gravity of dark matter versus the outward repulsive force of dark energy are balanced, and we can, so to speak, adjust each one and find the model that works the best, the one that matches the actual universe the best. And sure enough, the one that matches the actual universe the best includes dark energy. So this is also additional evidence that dark energy is real. Finally, if astronomers look at galaxy clusters, perhaps in nearby universe, a little more distant, a little farther, and the most great distances, that of course is telling them how galaxy clusters looked over time, doesn't it? The farther out we look, farther back in time we see. So essentially we can get a good idea of how galaxy clusters have changed over time by doing this. And interestingly, what happens is we find out that galaxy clusters were more massive early in the universe than today. Why is that? Well, essentially because dark energy is fighting against the galaxy clusters growing more compact. It's reducing the effect of dark matter, as we just explained, and therefore galaxy clusters have changed in a certain very specific way that requires dark energy. So I think you can see several lines of evidence, observational evidence, that establish dark energy as part of our universe. Well, finally, what could possibly be causing this effect? Quite frankly, we still don't know. This is a cutting-edge area of leading research today. There have been a number of ideas or hypotheses essentially proposed. One of the more popular ones takes us just for a minute into the very, very, very small realm of quantum mechanics. This field deals with particles at the very smallest scales. In fact, even smaller than most particles, we have even smaller concepts to consider, and that is the actual structure of space. Although we know that matter or energy cannot just mysteriously pop into the universe or out of the universe, there's a very interesting principle that has actually been confirmed experimentally, and that is that might happen if it happened for an extraordinarily brief amount of time. This is called the uncertainty principle. We can't be 100% precisely certain of the existence or non-existence of a particle if it were to appear or disappear quickly enough. These particles have been called virtual particles. In other words, empty space could literally create a particle and its antiparticle ever so briefly, as long as they annihilate each other quickly and disappear before you and I can measure them. This is quite of an interesting topic, isn't it? The point being, some have put forth the idea that perhaps if these particles were to appear into the universe, they could deposit a slight, tiny bit of energy to, in effect, stretch space before they disappear. So picture now at this extraordinarily tiny, tiny scale, these little virtual particles and their antiparticles pop into existence, give a little bit of a push or a little bit of a nudge or stretch to space, and then annihilate each other and disappear before we can even notice them. The point being, this might be one explanation for dark energy. Space essentially would be continually getting tiny little nudges from these particles and expanding outward. So this is one idea that is being pursued. There are some other ones, but at this point in time, dark energy has been confirmed as a real effect in our universe. So let's step back to the largest scales now, and let's just take a look at some of the things we've discussed in this lecture. We talked about the fact that there's this dark matter in addition to what we see as visible matter, and then we saw evidence for this dark energy. And since matter and energy can be considered the same thing, according to Einstein, how much of each is there? Well, it's an amazing discovery that there's actually very little visible matter in the universe. There's a moderate amount of dark matter, and most of the universe is dark energy. Quite an astonishing discovery. In fact, there's so much dark energy that it has now kind of gained the upper hand, so to speak. In other words, early in the universe, when the universe is smaller, matter is closer together, the gravity between galaxies is stronger, dark matter is dominant. It is resisting the original expansion of the universe, but as it does expand and the galaxies get farther apart, the gravitational effect of dark matter gets weaker. And now dark energy begins to establish itself and dominate and take the upper hand, so to speak, and become the dominant force. So just in very round numbers, we might estimate the amount of normal matter that you and I are familiar with is only about 5% of the total in the universe. Of that, only about 20% of that small amount is in actual stars. Other is just in the form of gas. Dark matter, approximately 25% of our universe overall, and dark energy would make up the remainder, 70% of our universe being dark energy. So we've really seen some amazing discoveries here in the last 30 to 50 years. Modern astronomy has really changed our perspective on the universe. Let's go ahead and do our summary of this particular lecture. We saw that dark matter is some unseen mass whose gravity really dominates galaxies. First discovered by the rotation of the Milky Way, and then confirmed in other galaxies by the rotation curves. Those curves did not decline with distance, but they remained essentially flat. Other evidence for dark matter included galaxy motions, the temperature of hot gas, and gravitational lensing. All of these confirming for us dark matter. We don't think it's likely large objects like dim stars. Instead, it seems far more likely that it's tiny particles. This has not been completely confirmed yet, but experiments are underway today to attempt to confirm the identity of dark matter. And because of its dominant gravity, it played a vital role, if not an essential role, in the formation of galaxies and even in the structure of today's universe. Then we saw that measurements of expanding universe We looked out and we saw galaxies at different distances. Astronomers measured their distances carefully with type 1 supernovae and found that the expansion of the universe is not slowing, but rather it's accelerating. And we saw several other lines of evidence that supported that as well. This effect is called dark energy, and one possible explanation may be that tiny virtual particles may literally pop into existence, give space a bit of a stretch, a bit of a push, and then disappear very quickly before any other effect is noticed. So we've really seen two major discoveries, two astonishing discoveries in modern astronomy. It really emphasizes that there is so much more for us to learn about our universe. In our final lecture in the course, we're going to examine the ultimate topic, the Big Bang, or beginning of the universe.